I'm Jiyeong. I am a condensed matter experimentalist in the physics department here at California State University, Long Beach. I am interested in the properties of very thin films. These very thin films are more than 1,000 times thinner than a human hair. When you layer materials as a thin film, you often observe very special properties you don't see from the bulk materials. Here are two bulk materials. One you know well, this is a nail made mostly of iron. Another you may not have seen before, this is niobium, element 41 on the periodic table. These two bulk metals have special properties. Iron is ferromagnetic. The atoms form atomic level magnets called magnetic domains. If you put a piece of iron in a magnetic field, these domains align in a certain direction. If you want to change the direction of magnetic domain of your iron, you have to apply a large magnetic field in the opposite direction. Niobium is not ferromagnetic, but it is a superconductor. If you cool it below a certain temperature, it will conduct electricity with no resistance. For my research, I make very thin films of materials like these. Let's step into my lab, then I will show you how we make these amazing thin films. I make my thin films on pieces of silicon, but this piece is too large, so the first step is to cut it with a diamond-tipped cutter. After cleaning, the silicon wafer is mounted on this special holder. The thin layers are deposited by a process called sputtering in this multi-target, ultra-high vacuum sputtering system. This is the sputtering vacuum chamber. The pressure inside is only 10 to the negative 7 torr. That is 1/10,000,000th of the pressure in this room. Now we're ready to make the first layer of my thin film. Argon atoms hit the disk of niobium, knocking off some of the niobium atoms, forming plasma. You can see the glow of the plasma. Positive niobium ions are attracted to the silicon wafer and form a very thin layer of niobium. To make a second layer, we close the shutter to the niobium and we open up the shutter to another metal. Today, the second layer is an alloy of iron and nickel called the pomalloy. In order to make this alloy, we open the shutters to two metals, iron and nickel, at the same time. How does one layer affect the properties of another layer? When the layers are very thin, you can get very different properties than you get with a bulk material. I use this PPMS, Physical Property Measurement System, to characterize the magnetic properties of the thin film at very, very low temperatures. This automated device can operate at temperatures near absolute zero and can change the strength and direction of the external magnetic field. I also use this smoke device that graduate student Han Ming helped construct to observe the magneto-optical Kerr effect. With this device, we observe how our thin films interact with light when they are under the influence of a magnetic field. We place the thin film here. These coils produce an external magnetic field. We shine light from this laser onto the sample. The light reflects and hits this sensor. As we change the strength and direction of the external magnetic field, we can change how the thin film interacts with light. We have many plans for future investigations. There are other ways of making thin films. We recently started making thin films on a layer of micro or nano polyester spheres on silicon wafers. There are many opportunities for undergraduate and graduate students to participate in my research. I hope you'll choose to study physics here at Cal State Long Beach.